Hello everyone. In this tutorial, we're going to give you a very high-level overview of TensorFlow versions 1 and 2. We cover how you can get started with Google Colab, we cover some basic concepts, and at the end, you will also see some very simple model implementations in TensorFlow version 1 and 2. And just as a side note, the slides and the materials you see in this tutorial are created by Bo, and he's one of the TAs of the course. And please note that all the programming related questions can be answered on Piazza or during assignment office hours. So let's get started. You can do the assignments using any versions of TensorFlow or PyTorch. However, please note that we will provide solution and answer questions only for TensorFlow version 1. However, we're going to do our best to provide support for TensorFlow version 2 as well. But the support for PyTorch, specifically on Piazza, might be very limited. In the next following slides, you'll see some cool machine learning applications. The first one is AlexNet, an object recognition model which won ImageNet competition in 2012 by a large margin. AlexNet was developed here at U of T by Alex Krzyzewski and Professor Jeffrey Hinton. And many believe that AlexNet triggered the wave of deep learning improvements that we've seen over the course of past few years. Online object recognition in computer vision is a cornerstone of self-driving cars, which many believe is the next disruptive technology. This strange effect called Deep Dream by Google, which you might have already seen it in your nightmares, is actually a very powerful way of visualizing learned features in convolutional neural networks. Generative adversarial networks, or GANs, are a class of very successful generative neural network models that can produce very high quality and real-looking images. Another very cool model in computer vision is called CycleGAN. CycleGAN is an image-to-image translation model, meaning that it can transfer the slide of one image to another. So, for example, as you see here, we have horses as inputs, and we get the style of a zebra on the horse. A very famous model in computer vision and in generative models is StyleGAN. StyleGAN is a specific generative adversarial network that lets you control over very high-level features and semantic of the generated image. And as you see, it's developed using TensorFlow version 1.5 by NVIDIA. Over the course of past few years, we've seen incredible improvement in reinforcement learning. And for example, we've been able to develop agents that can learn to play simple games like, in this case here, Flappy Bird or Atari games. TensorFlow is an open source library developed by Google for numerical computation, specifically for large-scale machine learning. TensorFlow offers many APIs in different languages, but what we're working here with is the Python API. But under the hood, many operations in TensorFlow is run in C++. So operations are, so basically we can write our codes in Python. However, in the very low level, they are written in and implemented in C++. And we can even use GPU as well as CPU. And the difference is, in CPUs, we have few cores, but each core is very fast and it is really good for tasks that need sequential computations, many sequential computations. However, in GPUs, we have thousands of cores. Each core is not as strong as cores in CPU. However, this will let us extremely parallelize tasks that can use parallelization, like for example, matrix multiplication. Okay, let's talk a little bit more about different versions of TensorFlow. TensorFlow version 1 was born out of Theano at 2015. And Keras is another high-level, let's say, framework implemented over TensorFlow. Using TensorFlow primitive operations, Keras implemented more, let's say, high-level implementations of different neural network layers. And you can easily stack different neural network layers, and it often offers predefined training loops. So the whole process of building a neural network, building your architecture, and training it is kind of more intuitive in using Keras. In 2019, TensorFlow 2.0 was introduced, where it combined Keras into TensorFlow, and it also provided a more intuitive way of executing your TensorFlow codes called eager mode. So why should we care about TensorFlow version 1 now that we have maybe a better version? The answer is you have extremely more online resources, books, and community supports for TensorFlow version 1 still. And you can learn a lot by lots of legacy codes out there. However, TensorFlow version 2 is easier to use, but you have less online resources and bug support. So this is where you should choose between version 1 and 2. We will talk about more about the differences of these versions, and you can decide which one to use for the programming assignments later on. PyTorch is another deep learning framework developed and maintained by Facebook, and over the past few years we've seen that PyTorch has dominated TensorFlow, specifically for machine learning research and for implementations of research ideas. And the reason is PyTorch is more self-contained, and it has great resources and, let's say, online forums and communities in the internet. To set up TensorFlow and implement the assignments, you will have two options. The first option is to use Google Colab. Colab is essentially a cloud-based Jupyter notebook environment that requires absolutely no setup. And above that, you're going to get a free GPU to use. And with only a Google account, you can easily search for Google Colab on Google, and there you go. You can start coding right away. Everything is installed in the cloud-based environment you see. You're going to have access to a GPU. A TensorFlow that is compatible with a GPU is already installed there. But the drawback is it is sometimes difficult to upload large data sets and use the data sets to train your model. For this course, it is strongly recommended that you use Colab because we're not going to deal with large data sets here. And aside that, you can also set up TensorFlow in your own machine. However, it's sometimes tricky to set up TensorFlow to work with your GPU, and it might take some time. So option 1 is strongly recommended here. However, we will cover how to, let's say, install in your local machines in the appendix section of this slides. To get started with Google Colab, you need to open up colab.research.google.com and create a new notebook. And there you go, you can have access to an online Jupyter notebook where in the environment many useful and famous libraries like NumPy, scikit-learn, pandas, matplotlib, TensorFlow, both versions, and even PyTorch is already installed. If you want to have access to GPUs, you need to go to Runtime menu, select Change Runtime Type, and from them, select GPUs. Okay, so if you import TensorFlow by default, you're going to have TensorFlow version 2, specifically TensorFlow version 2.4.0. If you want to use TensorFlow version 1, you need to first, before importing TensorFlow, you need to first run this magic function, TensorFlow version 1.x. And then you're going to have access to latest TensorFlow version 1, which is 1.15.2, as you see on the left. The simplest unit of data in TensorFlow is called a tensor. Tensor is a multidimensional numerical array. Tensors can have different ranks, meaning that they can have different number of axes or number of dimensions. The shape of a tensor is the number of elements along each dimension of a tensor. And the type of the tensor, that is called d-type, basically tells you what is the data type you have on each element. For example, this can be integers, this can be floats, or even this can be, let's say, strings or characters. For example, an image from MNIST dataset will look like this. This is a single 28 by 28 image. The tensor containing this information has rank 2, and if you look at the shape of this tensor, you'll see that this is 28 by 28. And the type, or the d-type of the elements of this tensor is integer 32. If you have multiple images, you're going to stack them together into the first axis. So remember that the batch dimension is always the first dimension of your tensor. So this is kind of like a standard to keep in mind. So for example, multiple MNIST images will be stored in a tensor of shape n by 28 by 28. If you have color images instead of grayscale images, you're going to have an additional dimension at the end, which will store information about red, green, and blue pixel values. So in this case, if you have n 28 by 28 color images in a tensor, the shape of the tensor would be n by 28 by 28 by 3. If you want to create tensors, you'll have multiple options. The simplest case is to use tf.constant. This will instantiate a constant tensor for you. For example, in this case, x is a constant tensor holding the value of 1. And as you see, the d-type here is inferred from the value 1, which was an integer. tf.variable instantiate a variable tensor, whose value can be changed. This is usually used for trainable values, such as weight and biases of your neural network. You can see another example here. You're going to have a 1 by 1 tensor holding values 1 and 2. And again, the d-type is inferred from the initial value of the variable. So these two constant and variable tensors are the same between TensorFlow 1 and 2. However, in TensorFlow 1, we have an additional type of tensors called placeholders. tf.placeholder instantiates a container whose value will be provided when running the program. And this is usually used for the input data to our architecture and, for example, for training labels. So when you are training your models, you can input different values into a placeholder. For example, as mentioned, this can be your input images or your input labels. And you will see later on that you're not gonna need any placeholders for TensorFlow version 2 procedures. If you want to fill a tensor with an initial value, you can use tf.fill, and you can specify the shape of the tensor you want. For example, if you want to create a 2 by 2 tensor filled with value 1, you can use tf.fill. You will specify the shape and the initial value for all the elements. Another very useful way to create tensors with random values is tf.random.normal. This will create a tensor with a specified shape, and the values will be filled using a random variable with, for example, in this case, with specified mean and standard deviation. For example, in this case, we're going to create a random tensor with a shape 2 by 2, and each element is instantiated from a normal random variable with mean 5 and a standard deviation 10. This is very useful for initializing weights of your neural network. For example, you can initialize a TF dot variable with normal elements. You can get the d-type of any tensor using tf.tensor.dtype or directly access the d-type property of any tensor, like here in this example. We have first instantiated a tf.variable with a floating point initial value, and if we access the d-type property, we will see that the d-type that TensorFlow assigned to this tensor is float32. And this is the default d-type that TensorFlow assigns to any variable with floating point initialization value. But note that incompatible type conversion error is very common. For example, in this piece of code, you see that I'm adding two tensors. One is initialized with value 1.0, another one is initialized with value 2. So the first one is by default float32 tensor, the other one is int32 tensor. And you cannot add these together because they don't have the same d-type. So please note that this very important issue, that keep in mind that you have to use a consistent d-type over all your architecture. And it is basically suggested that you always use, for example, tf.float32, which is the default. You can also cast different d-types to each other using tf.cast. For example, in this case, you see that we are casting this float32 into float64 using tf.cast. To access the shape of a tensor, you can use getShape function or simply the shape property. For example, here we have a 2 by 3 tensor, and if we print x.getShape or simply x.shape, we get the shape of the tensor. The size of a tensor is basically the total number of elements in a tensor. For example, here x.size will return 6. So indexing tensors in TensorFlow is pretty much the same as array indexing in NumPy. So if you're familiar with array indexing in NumPy, like advanced indexing, like Boolean indexing, you're good to go. So they're pretty much the same. And here you can see a very simple example. For matrix multiplications in TensorFlow, you can use tf.matmul. tf.square is another useful method, which returns element-wise square of all entries of a tensor. You can also use double star operation, where very similar to NumPy, it will return different powers, different element-wise powers of any tensor. Another two very useful methods in TensorFlow are reduce sum and reduce mean. Reduce sum simply sums across a given axis. If no axis is provided, it will sum entire tensors. For example, let's say we have a simple 2 by 3 tensor. tf.reduce sum of x will return the sum of all elements. However, if you specify axis, for example, in the next line, we have a specified axis 0, the sum will reduce axis 0. It will remove axis 0, or it will sum all the elements across axis 0. So at the end, as you see, you're getting a rank 1 tensor. We can also keep the dimensions. For example, because we had the rank of the original tensor was 2, here the rank of returned reduced sum is also 2. You can have the same thing with tf.reduce mean as well. Okay, let's talk a little bit about broadcasting. If you're familiar with NumPy, you have already heard of broadcasting. The same concept of broadcasting in NumPy is already there in TensorFlow, and it is perhaps one of the most fundamental strengths of numerical computation in NumPy and in TensorFlow and many other numerical computation libraries and frameworks in Python. So this is an extremely important concept, so you should be very comfortable with it. It's kind of awkward at the beginning, but once you get used to it, you see its power. So keep in mind this very simple rule. Whenever you're having an element-wise operation between two tensors, like for example addition, like subtraction, like division, any element-wise operation with two tensors will trigger broadcasting. Once broadcasting is triggered, NumPy or TensorFlow starts comparing trailing dimensions and works its way forward. And we call two dimensions compatible when they are equal or one of them is 1 or simply empty. So let's see what I mean by that. We have three examples here. The first example, we are adding two equal-sized tensor. Both are 4 by 3. What happens here in broadcasting is that TensorFlow compares trailing dimensions, here in this case 3. So we have 3 in the first tensor, we have also 3 in the second tensor, so they're compatible, we are good to go. Next, we have 4 and 4, they're equal, so they're compatible. So we can just add values element-wise. In the next example, we're adding a 4 by 3 tensor into a one-dimensional tensor of shape 3. So what happens here is that TensorFlow starts comparing dimensions, comparing trailing dimensions. So what we have again here is that 3 is equal to 3. This dimension is compatible in broadcasting. The next dimension, we have 4 in one tensor, we have nothing in the other tensor. So what happens is that this dimension for the second tensor will get repeated. And as you see here, this is a visual, let's say, understanding of what happens in this case. The second tensor gets repeated in the first dimension. And then, so the second tensor is also a 4 by 3 tensor. Now we can have our element-wise addition. So this is very useful if you want to add, for example, add a vector or add an array to each row of another array. So here, let's say we have a matrix and we have a vector, and we want to add that vector to each row of this matrix. We can use broadcasting instead of manually repeating this. TensorFlow will take care of this repeating. Let's see another example. Let's say we have a 4 by 1 tensor. We want to add it to a 1D tensor of shape 3. So we have 4 by 1, we have 3. What happens is that the first dimension, the trailing dimension is, for one tensor is 1, for the other one is 3. So 1 will get repeated to become 3. The other dimension is 4 and empty. So for the second tensor, we will repeat the first dimension to get 4. So here, as you see, both tensors at the end of this repetition problem procedure, they will become of the same size or shape. So basically, at the end, we have two 4 by 3 tensors that can get added element-wise. Here again, you're seeing a simple example of broadcasting where you add a number to a tensor. That tensor can be a vector or a matrix. Here, this is very intuitive that this number will get added to every element of that tensor. However, under the hood, this is the rules of broadcasting that makes this possible. You can also get broadcasting errors, where two arrays are not broadcastable, which means the dimensions of those tensors cannot fulfill the conditions that I mentioned in the previous slide. I strongly recommend that you read about broadcasting online on TensorFlow or in NumPy website. I've added a link to the NumPy webpage that discusses broadcasting. This is very important to be comfortable with, as I mentioned earlier. Otherwise, you're going to get errors that you cannot understand. In TensorFlow version 1, by default, your models are built using a computation graph. So in a usual procedure of creating and running a model, you first construct a graph consisting of tensors and operations. Next, you will instantiate a session and run the graph you created before. We will see the examples of how you create your computation graph and how you can even visualize that graph. But why do we need a computation graph? This basically lets TensorFlow to understand how to parallelize your computations easily on a GPU or even on a CPU. So let's start with a very simple example. Let's say we want to evaluate the value of a function x squared y plus 2 and x equals 3, y equals 4. We want to evaluate the value of f at this point. So what we do in TensorFlow version 1 is that first we import TensorFlow. Of course, if you are in Google Colab, you need to first ask Colab to import TensorFlow 1 for you using that magic function I described before. Next, you create your computation graph. So what's happening here is that I'm creating two variables, x and y, with value 3 and 4, and then I'm creating another variable, f, which basically implements that function for me. Note that in TensorFlow 1, we don't have access to the value of f at this stage, because what we have done so far is that we only created the computation graph. We have not run the graph yet. So if you want to get the value of f at this point, you're going to get an error. So how can we run the graph? So in order to run our graph, this is what we always do. First, we create another node in our graph called initializer node. What this node does is that it basically initializes all the variables in our computation graph. So with tf.global variable initializer, we create another node that basically can initialize our variables. Next, we create a session with tf.session. Once we created the session, we can run any node on our computation graph and access the value of it. For example, here, what we are doing is that we first run this initializer operator, then we can have access to the value of f using sesh.run f. There is an alternative version here that you can create a session, an interactive session, at the beginning of your code. Then you can create your computation graph, and using that session object, you can run any node on the graph that you like. But remember that at the end, you need to close that session. What this with block does for you is that it takes care of closing the session, even if you encounter an error. The good thing with TensorFlow is that you can visualize the computation graph using TensorBoard. The details of using TensorBoard are discussed in appendix. If we visualize the computation graph of this very simple example, we see that the variables are just nodes in this graph. And again, each operation is another node. So what happens is that you see we're starting with x, It is initialized with value 3, as stated here. We multiply x with x again in the first multiplication node. Then it gets multiplied by y. Then the whole thing is added to y. So up to this point, we have x squared times y plus y. And at the end, we add 2. So in TensorFlow 2, we don't have to deal with computation graphs and then running that computation graph. And we can get the intermediate results of any variable immediately. This was called eager execution mode in TensorFlow version 1, but it is by default, this is actually the default behavior of TensorFlow 2. We're going to see what that means. So let's implement the previous example using TensorFlow 2. So as before, we create our variables x and y and define our another variable f. So if we access the value of f here by using printf, we see that it will tell us that, okay, f is a tf.tensor with value 42. This is what we didn't have access in TensorFlow version 1. So another nice thing in TensorFlow version 2 is that we can convert the value of a tensor into a NumPy array using the function NumPy. So f.NumPy returns a NumPy array with the value of the tensor f. So far, we've seen the differences in execution pipelines of TensorFlow 1 and 2. In TensorFlow 1, we had something called placeholder. Placeholder do not possess a value at the construction phase of the graph. And they exist only in TensorFlow 1. And we use them to feed the training data or the training labels during the runtime of a graph. Note that we only need to know the D-type of a placeholder. And as I said, we feed data as a dictionary to the placeholder at the same time when we evaluate the graph using session.run. And this is typically the syntax we use. We say session.run, some node in the graph, and we add this dictionary that contains placeholder names and values. Let's see what that means. In our simple example, let's say f is x squared y plus some constant value c. And we don't have c at the beginning, and we want to feed c into the graph later. What we do is we first, like before, instantiate the variables x and y with their initial value. We next define a placeholder c, and we create f using x, y, and c. Like before, we should create our initializer node in the computation graph. Next, we instantiate a session object. Right after this, we run the initializer node. And then when we want to calculate the value of f, here we need to specify or we need to feed the value of our placeholder c. As you see here, after f, we have another input argument, which is a dictionary with keys, the name of the placeholders we have, and values, actually, the value of the placeholder. So here again, we see the previous result of 42. If we want to simulate this behavior in TensorFlow version 2, meaning that we want to feed in some constant value like c here in this case, what we can do is that we can simply, pretty much like what we do in pure Python, we can simply define a function using x, y, and c, and at the time of calculating f, we need to basically input the value of c as an input argument to function f. as you see in this example. Up until this point, we discussed how to create your computation graph, for example, in TensorFlow version 1, or in version 2, how to simply just define your model. But what we need to do next is to optimize our model, meaning that tune the weights and biases of our neural network. This is called optimization in TensorFlow. So suppose that we have function f and we want to find a minimizer of this function with respect to its input x. Gradient descent is the go-to algorithm in machine learning here, when we iteratively minimize the value of our function by moving toward the negative of the gradient of our function. In TensorFlow 1, as you can imagine, we need to create an optimization node in our graph. Like here you see, we define an optimizer node using tf.train.gradient descent optimizer, and we need to specify the learning rate. Next, what we do is that we can call this optimizer's minimize function. So this training operation is a node in our graph. And once we created our session, we can call this training up node. And this will just run one step of gradient descent for us. In TensorFlow 2, on the other hand, we use something else called gradient tape. Let's again explain this with a very simple example. Consider we have function f log of x squared, and we want to find a minimizer of this using TensorFlow 1. So what we do is we first instantiate a variable with an initial value. Next, we define our function f using tf.square function. The next thing we do is that, as discussed before, we instantiate an optimizer object, for example, in this case, a gradient descent optimizer, and we call the minimize method of this optimizer. This gives us a node in our computation graph called train. We will call this node train later once we created our graph. So as always, before creating the graph, we need an initializer node using tf.globalVariables initializer. So we create our session. Inside the session, always, the first thing we do is that we initialize all the variables. So at this point, x gets its initial value of 5. What we do next is that inside the for loop, we just need to run the node train here. So each time we basically run this node train, it will perform one step of gradient descent for us. In TensorFlow version 2, we can calculate the gradient of any function with respect to any of its arguments using tf.gradient tape. So what we do here is that, let's say we have defined a variable with initial value of 5. In a with block, we instantiate a gradient tape and we call it g. G.watch will tell the gradient tape that the value that we want to take gradient with respect to is x. Next, inside this with block, we define our function f using x. And we can access the gradient of f with respect to x using g.gradient. Now it's easy to build upon this and create our own stochastic gradient descent. We have, up until this point, we have easily calculated our gradient. What we need to do is to just implement the gradient descent. We move toward the negative direction of the gradient. Like the example in TensorFlow 1, you don't have to implement SGD by yourself. You can use tf.keras.optimizers.sgd. And if you call the minimize method of this optimizer, it will automatically take the gradient and applies one step of gradient descent for you. So you can basically compare this code with the one that we had in TensorFlow 1. The only difference here is that we don't see the sessions and the initializer of the variables. All the other things are actually the same. However, this is more intuitive since it's like normal Python execution flow that you write down your codes and you can access any value at any given line of your code. Loading famous datasets into TensorFlow is really easy. You can use tf.keras.datasets. And there are existing datasets, well-known datasets like C410, C400, MNIST, Fashion MNIST, and a bunch of others. For example, you can load C410 by running this line of code. And as you see, you can get training and test splits here, and you can specify the split that you want here as well. There is another way to load datasets using TensorFlow datasets. We usually import this as tfds. With tfds.load, we can load any dataset we want, and it basically takes train test splits as an argument. However, it's kind of easier to use Keras datasets instead of TFDS, but here you will have more control over how to load your data and how to feed your data into your models. One of the best resources to learn more about TensorFlow is to look at TensorFlow official tutorials. And you can see best practices and you can see implementing many simple to complex models in tensorflow.org/tutorials.